Alright, thanks for watching. So today we're going to be talking about using vectors on motion diagrams. And we're going to start off by remembering the way that we've dealt with velocity and acceleration up until this point. So up until now, velocity has been a one-dimensional concept. We've either gone in the up direction or down direction, left or right. And the formula that we've had is velocity, say in the x direction, is equal to the delta x over delta t, or the displacement over time. And velocity has been a number, and displacement has been a number. Now all of that is going to change as we expand our idea and our concept of velocity. So that was then, this is now. Now we're going to be dealing with two dimensions, and velocity is a vector and displacement is a vector. So our new formula is that velocity, the velocity vector, is equal to the displacement vector divided by time. Or we can, since delta t is just going to be a number, we can pull that out as a scalar and say 1 over delta t times the displacement vector, which anytime you have a scalar multiplication, it's just going to be that scalar multiplication times the magnitude, and then the direction of the velocity vector is going to be the same direction as the displacement vector. So as I mentioned a moment ago, before velocity was just a number, displacement was always just a number. Now velocity is going to be a vector, and what that means is velocity is going to have both an x and a y component. Displacement is going to have an x and a y component. Also, acceleration. If we think about then and now. Then, up until now at this point, acceleration was one dimension and had the formula, say the acceleration in the x direction was delta vx over delta t, or acceleration in the y direction was delta v over, or sorry, delta vy over delta t. Now velocity is in two dimensions, or sorry, acceleration is in two dimensions. It's a vector, and the formula that we're going to use is acceleration is equal to delta v, the change in the velocity vector, over delta t. And what that means is delta v is going to be the final velocity vector, v sub f, minus the initial velocity vector, v sub I. We have also written that as v naught. And that whole upper portion right there is one of the reasons, in fact the primary reason, why we learned vector subtraction, so that we can figure out what is the direction of our acceleration vector going to be based on this subtraction. So let's go ahead and do an example here. So let's say we're given an object's motion diagram, 3 dots just like that, and then what we can do is we can actually draw the velocity vectors there, connecting the points. So we've got point 0, 1, and 2, and then velocity naught, or the initial velocity, and then v1 representing this vector right here. And then let's say we're asked to find the acceleration vector. So we set up the problem by saying, okay, the acceleration vector is going to be delta v over delta t. And in this case, that's going to be v1 minus v naught over delta t. And what we're going to do is we're going to draw the diagram. We're going to draw this vector subtraction in order to find the direction of our acceleration vector. So you can see, first off, we'll draw v1, since that's the one that we're starting with. Then we'll draw negative v naught. That's how we do vector subtraction. And then just connect the dots there. Connect the beginning of v1 to the end of negative v naught. So this new vector is v1 minus v naught. So then we know that our acceleration vector at this point right here is going to be pointing in that direction. You can see I've got it off just a little bit, but you get the idea. And this is a pattern that we're going to see. That is that the acceleration vector points inside the turn. And we're going to actually apply that now to circular motion. So let's say that you are given an object moving at a constant velocity in a circle. So you go ahead and draw a circle, and you've got the different dots going around here. So the object will start right up here, and it travels along the circle, and this is where it's going to be at different moments. And we're asked to find the velocity vectors and the acceleration vectors at each point. So we'll go ahead and draw some really large velocity vectors there. Well, it's almost covering everything up. But anyway, there's the first velocity vector from point 0 to 1. V1 here, V2, V3, V4, and V5. Then what we need to do is now we're going to find the acceleration vector, and we're going to first focus in on this point right here, point 1, or the location called 1. And we'll write the formula. The acceleration at 1 is equal to v1 minus v0 over delta t. That's our formula, our vector formula for acceleration. And this is just going to be sort of for demonstration purposes. I'm not going to actually measure these and then find the length of those and then divide it by a delta t that I haven't decided yet or anything like that. What we're going to do is we're just going to do this vector subtraction, and we're going to find the direction of the acceleration vector because you'll see something neat as we do that for all the different points around the curve. So we're just going to do that vector subtraction to find the direction that this vector is in and not really worry about the magnitude so much. So once again, we'll draw v1, the initial that vector part right there, then negative v0, that takes care of this, and then just connect the dots from the beginning of v1 to the end of negative v0. And there's our difference vector, and that's going to be the direction of the acceleration vector at this point right here. If we continue on and focus in on point 2, then the acceleration vector is going to be v2 minus v1, so this velocity vector minus this velocity vector divided by delta t. So start off by drawing v2. That corresponds to this v2 right here. Then negative v1, obviously see, if you look over here, v1 goes down, so negative v1 is going to be going up. And then we just connect the dots. So the beginning point of v2 to the end point of negative v1. And then over there we just do that. So if we carry this trend all the way through, what actually happens is that the acceleration vector at each one of these points ends up pointing towards the center. So from this we can draw the conclusion that an object moving at a constant velocity in a circle has acceleration towards the center at all points on the circle. So no matter where it is, as it's traveling around the circle, it has an acceleration vector that is pointing towards the center. And what that does is that actually kind of tends to conflict with our idea of what acceleration means, because we're traditionally used to thinking, okay, acceleration means a change in speed. However, if we're going to define acceleration as a change in velocity, which we are, then this leads us to this new concept. That is that acceleration occurs when there's a change in velocity. And since velocity is a vector which has two different parts, magnitude and direction, then acceleration can occur when an object changes either its speed, which is magnitude, or its direction. And wow, I did a crazy typo right there. Changes. That's pretty strange. So anyways, the point is, velocity is two parts, magnitude and direction. And if either one of those change, then acceleration exists. So what we're most familiar with is with a change in speed. But, as we found, a change in direction, even if it's still going at the same velocity, a change in direction means that there is acceleration. Now, the acceleration vector always points towards the center of the circle if the object is traveling in a circle, or inside the turn if it's even just a part of a circle or an arc. So you can see if the object is traveling just in some sort of curved motion, or even if it's changing direction at all, the acceleration points inside. The acceleration vector points inside there. Alright, and that's going to conclude discussing our motion diagrams now with vectors. Thanks for watching.